Our first speaker is Jerry Mabary, Sandhill Scientific. He's Vice President of Technology Development. He holds 2 patents for developing mediums for use in esophageal function testing. So any of those with GERD, you know what I'm talking about. His topic is non-invasive liver stiffness assessment. Jerry, if you come up, appreciate it.
Good afternoon. I would first like to confess I don't know any jokes, so my apologies right up front. I would like to thank the organizers for inviting me to speak. I am particularly gratified to see a group working so hard and so effectively to get out the latest information on therapies and diagnostics. I wish all patient groups were as effective as the one that I've been witnessing here today. So my congratulations to your group and all the participants. I would like to give you an overview on some new advances in the field of diagnosing liver disease. And I would first like to stress that there's a tremendous amount of activity in liver disease in general, both on the diagnostic and therapeutic side. There are some very large and growing demographics in the disease groups associated with the liver. The one that all of you have probably seen very prominently in the news, it appears almost on a daily basis, is hepatitis C, or HCV as the acronym is called. The reason there's so much focus on liver disease today is because the Center of Disease Control took a position 1 year ago that all of us baby boomers, most of the people I see are in my group. All of us baby boomers, according to CDC guidelines, should be screened for the hepatitis C virus. They're looking for the antibody in your blood. It is now well received and respected that more than half of the people that have hepatitis C don't know it. And we can't deal with a disease, an epidemic, if you will, unless we can cut the transmission cycle. So because of this focus on identifying those of us with hepatitis C and aggressively treating that C to break the transmission cycle, the liver is getting a lot of attention. And you indirectly benefit from that because there are advancements that are being made that ordinarily probably wouldn't get the attention necessary for these breakthroughs. So let me begin, if I may. For centuries, many of you have probably been monitored for liver disease. Just so you know the history of diagnostics in liver, for thousands of years, physicians have merely palpated the abdomen to see if the liver is hard, to see if it's stiff, because it's well accepted that stiffness is a key physiologic parameter for assessment of that tissue. All we have done with this latest breakthrough in the diagnosis of stiffness is we have developed a scientific way to objectively assess the stiffness of the liver and to reproducibly be able to test the liver. This gives us an important dual capability. First of all, we have a simple point of care technique where immediately patients that are first diagnosed with chronic liver disease can have an immediate diagnostic that determines the extent of damage to the liver. Secondarily, we have a test that can be used longitudinally. By that I mean, imagine a patient being tested on a regular basis, perhaps once per year, perhaps once every 2 years, and being able to monitor the status of that liver over time, because it's probably important not only to know the stiffness of the liver today, but to track changes over time. That would give us the capability to track disease progression and to track therapeutic response. So what I'm talking about today is really founded in those basic principles. The name of the technology that I'm going to tell you about today is technically called, from an operating principle standpoint, vibration-controlled transient elastography. Now, that's a mouthful. We like to use complicated algorithms in the diagnostic field because it makes us look more intelligent when in fact we're not. But each of these words in this descriptive term is stating something about how the test is done. Now, I would like to state up front that I am an employee of Sandhill Scientific, and therefore I'm disclosing that I have a commercial interest in this product. My goal is to inform you, not to convince you of anything. So I do want to disclose right up front that I am intimately involved in this technology, and in fact I am the person that brought this technology to the United States. Now let me explain the operating principle. This is a probe. It looks very high-tech, doesn't it? It's quite space age. This is a probe that's used to do the test. Now, let me explain the business end of this thing we called a probe, and you'll notice that it's being called by the term VCTE probe, or vibration controlled transient elastography. Now, I want to explain the basics of this so you know what this is about. The tip of this probe is actually a mechanical actuator that moves. So when a clinician presses a button here to take a measurement, the tip of that probe actually makes a fast forward and back movement to establish a slight vibration that's going to travel through the liver. I will explain that more in just a moment. Second of all, the tip of this probe is also an ultrasound crystal, which is to say the tip of that probe is capable of transmitting ultrasound and receiving ultrasound. That's a lot to absorb. Let me do it a little more simplistically. So the steps to do a VCTE test are as follows. We first induce a shear wave in the tissue. A shear wave is a vibration, and then we're going to measure how fast that shear wave moves through the liver. And then finally, we're going to calculate stiffness. Let me cover each of these in better detail. We obviously have a liver here. Anyone that doesn't recognize that should be in the lecture down the hall. And this, of course, is our VCTE probe. We place the probe above the center of the liver. You'll notice this is lined up with the center of the liver mass. And when we take a measurement, we're going to have that little vibration of the tip of the probe that I was just explaining. Let me go ahead and vibrate the tip of that probe, at least in PowerPoint terms. And there is a wave moving through the liver, and I'm expressing that wave down below. Let me play it again. If you watch down here, this is movement and this is time. So when we vibrate the tip of that probe, we're going to send a little wave through the liver. Now you're probably wondering, what does he mean by this wave? All right, let me make it even more simple. Take a look at this little wireframe movie that I'm just playing over over and over again so that you can see it. Now, what you will notice here is that there's a wave moving from the left side of the screen to the right side of the screen. And you will notice that as this wave moves across the screen, that it's moving at the same speed all the time. And I want you to notice that this wave has a leading edge and it has a trailing edge. That looks a lot like if I were to throw a pebble in a pond, you would get a large ripple that would move concentrically away from that point of impact. Now, in the case of throwing a pebble into a pond, I'm actually using that pebble striking the water. That's inducing a shear wave. And then the shear wave moves away from where that force was applied. This is the same thing. I'm just showing it in a single dimension instead of showing it traveling out in a concentric circle. Okay, so now we know what a shear wave looks like. By the way, some of you are saying, wait a minute, that looks like an earthquake movie. That actually is an earthquake movie, but it perfectly represents what a shear wave looks like when it travels through tissue. Okay? Now, so far, we've placed the probe over the center of the liver. We've vibrated the tip of the probe to induce a shear wave, and the shear wave is moving away from where we induced it. It's traveling away from the tip of the probe. Now, what I need to know from a physics standpoint is how fast is that shear wave moving? Well, it turns out that's why we have ultrasound incorporated into the probe. We're not using ultrasound to do imaging. We're using ultrasound as our shear wave speed detector. Ultrasound is our radar gun. Okay? So what we're doing is, from the tip of the probe, we are transmitting ultrasound, and the ultrasound goes out, and it hits that wave, which is out here somewhere in the liver. And that wave reflects that ultrasound back to the probe. Remember, the tip of that probe is an ultrasound transmitter and receiver. Now, we know how fast ultrasound moves in liver tissue. That never changes. So if I know that I send out a burst of ultrasound at some point in time, it traveled out, bounced off the shear wave, and traveled back. Based on the amount of time it took for that wave to go here and come back here, I know where that shear wave was at that instant in time. Now, if I keep sending out ultrasound in bursts, I know that that shear wave is there now, and there now. I just measured its speed. Okay, let me put it together one last time. We vibrated the tip of the probe and induced a shear wave. We measured the shear wave's speed with ultrasound. Now, don't panic, stay in your chairs. We're going to produce something that looks like this. This is a mathematical reconstruction of what we did. I'll explain it in very simple terms. This is depth below the skin. The skin is up here. You can see this is 25 millimeters below the skin. This is 65 millimeters below the skin. And this is way down deep in the body. This is time. This dark shadow that you see moving diagonally, that is the shear wave moving through the tissue. So what you have then is, we merely measure how fast that is going, which is a time distance calculation, because how far something goes in a certain amount of time is called speed, isn't it? We're just measuring speed. Now for the key method that we use. It turns out that we can thereby, using this formula of physics, remain in your seats, do not run for the door. We use this formula of physics to calculate stiffness. This is a well-established formula. We just plug in what we just measured, and out of this comes the stiffness of the liver in a unit that's called kilopascals. We saw that on the report I was looking at just before I came up. Okay. Now you're saying, Jerry, okay, that's fantastic. You did a whole bunch of physics stuff, and it appears, even though you're not saying this clearly, but it appears that you're trying to assess the health of the liver based on its mechanical properties. You're not using some sort of chemical-based test. You're not doing a biopsy where you go in and take a core sample and you look at it under a microscope to see if there's any fibrosis there. You're fooling around with some kind of a mechanical property technique here, and you would be accurate in that statement. We're assessing the tissue based on its mechanical property to transmit a shear wave. It turns out, well-established physics concept, that a shear wave moves more rapidly through stiff tissue than it does through healthy tissue. So what I'm telling you is, if you were to measure the stiffness of something like a marble, which is very, very stiff, a shear wave would move through that tissue very rapidly. If you were to measure how fast a shear wave moves in healthy liver tissue that doesn't have fibrosis, it would move very slowly. Now, what I'm showing you here are 4 different liver tests. I want you to notice across the top, I'm showing you test data from 2 healthy livers, and across the bottom, I'm showing you data from 2 very stiff livers, stiff to the point that they're termed cirrhotic. Now, you're not used to looking at these, so I'm going to fly in some cheaters for you. I'm going to fly in those white lines. Now, those white lines are the shear wave moving through the liver tissue. And I don't know if you can tell from the slope of this, but that shear wave is moving slowly, and so is that one. That shear wave is moving fast, and that one's moving fast. Can you see that? They're covering a greater distance in a shorter period of time. They're moving fast. The stiffness of this liver is 4.1. That's a very normal value. This one's 5.5 kilopascals, also a very normal value. And these are very high numbers because those livers are cirrhotic, and therefore the shear waves move through them rapidly. High-speed shear waves. Okay. Now, what's the application of this assessment of liver tissue based on its mechanical properties? These are all the diseases that are commonly diagnosed using the FibroScan VCTE technology. I already spoke a little bit at the open about viral hepatitis. I'm sure you're all familiar with hepatitis C and hepatitis B. It's very routine that the status of the liver is diagnosed using this technique in viral hepatitis. Another very rapidly growing disease group is those fancy letters there. Remember, we use acronyms to try to look intelligent. Those fancy letters are basically describing fatty liver disease. You probably noticed that about 1/3 of the patients in our country are clinically obese now. Fatty liver is a huge public health concern, and it has a strong impact on liver health. And so there's a lot of emphasis on diagnosing fatty liver disease to assess the liver to see if it is damaged. Of course, we're all familiar with alcoholic liver disease, heavy consumption of alcohol over a long period of time. I call that Mickey Mantle disease. I think he was the poster child of alcoholic liver. And then finally, of course, our concern. Okay, you're probably asking, okay, this is the first I've heard of this VCTE to assess the liver based on its mechanical properties. So let me give you just a little feel for the validation of this. Obviously, anything that's used diagnostically in this country must be well validated, otherwise it wouldn't be on the market, and that's a good thing that protects you and us. So this device has been actively used in Europe for 13 years. The technology is actually originally French technology. It was developed and first described as part of a PhD dissertation in Paris. And the inventor is still with the company. He's a good friend of mine, and he's adding new technologies in the background that maybe I can come back and tell you about in 3 to 5 years. But this is French technology in its origin, and because it's been on the market in Europe for 13 years, it is very well described in the peer-reviewed scientific literature. There are in excess of 850 peer-reviewed publications, and 1 or 2 new ones appear every week. Of this group, about 70 of these publications are from the United States, and there's very, very active research in viral hepatitis and fatty liver disease in the United States. The focus of all this scientific literature is basically validating the usage of VCTE in 3 ways, which I described at the beginning of my talk. The first is to get a snapshot of the stiffness of the liver at any time, and then secondarily, once this baseline value has been established, being able to track disease progression and therapeutic response. But obviously you can't do these without first having a test and establishing a baseline value. I'm often asked about what's the published accuracy of the test, which is a very, very appropriate question. I'm describing here in this rather complicated slide, this is a snapshot summary of the literature, and this is describing a series of publications that includes somewhat in excess of 10,000 patients, and it's across all of the liver disease groups. And what it is showing you here for an accuracy, you probably don't know the statistics of things like AROC, but it's a statement, it's a blended statement of accuracy that includes both sensitivity and specificity of a diagnostic test. The accuracy, or AROC if you will, in identification of cirrhosis, you can see is averaging there about 0.95. So what this is saying is, if you compare the diagnostic finding of this test with the diagnostic finding of a biopsy, the 2 tests will agree 95% of the time in the identification of cirrhosis. 5% of the time they will not agree, and obvious question then is which test was right, and to that I'm afraid I must say, who knows? Because you have no other test that serves as a point of reference. So appreciate that this technology was validated for accuracy by comparing it blindly to biopsy, because biopsy was the only existing test that we could compare to and produce scientific values. In lesser diseased patients with significant fibrosis, Some of you probably are familiar with the Medivir scoring table, F3. There's an accuracy there of about 85%. It's always true with a diagnostic test that it's easier to be right if you're diagnosing someone with significant damage. It's a harder task to diagnose someone with early stage damage. So these are very normal statistics in terms of diagnostic accuracy. So I just want you to understand that the test is well validated, and this is the kind of information that was used to get FDA clearance. Okay. I'm really hesitant to give you reference values, so I really want to qualify this up front. As a developer of diagnostic technology and as manufacturers of this product, we cannot, do not, will not, and should not give you threshold values, because interpreting the values that are produced in one of these studies is complicated, and it must be interpreted by a physician in the context of full information. What is always done in medicine is you use as many tests as you have available to you, and you assemble all the information you can get, and then a physician makes a professional judgment on whether or not this is a stiff damaged liver or not. So do not take these as literal values that somehow could be used by an uninformed person in an uninformed environment. But I would like you to know I can cite literature sources which anyone that has access to the internet can find. All I'm doing is saying, here's a reference if someone were looking for one. You will see that the median stiffness here is shown to be 5.5 plus or minus 1.6. So if you believe this study, which is your judgment as to whether or not you believe it, if you believe this study, it's basically saying that normal liver stiffness is 4 to 7 kilopascals. Okay? Okay. All right. Now, as I mentioned earlier, interpreting any diagnostic test is complicated because nothing is simple, nothing is straightforward. It turns out that liver stiffness is impacted by more than just fibrosis. Now, I kind of implied, and you probably thought as I was talking, this mechanical test that these people have for assessing the status of the liver, the stiffness of the liver, it's really an indirect way of determining fibrosis. To some extent, you're right, and to some extent, you're wrong in such a statement. The primary variable that we're assessing when we do this test is the presence or absence of fibrosis, fibrous tissue in the liver, which of course is a fancy way of saying a liver that's been damaged, and some of the functional cells of the liver have been replaced by scar tissue. And of course, scar tissue is not functional. It can't perform the metabolic functions that a liver cell can perform. So as scar tissue develops, that means that more and more of the liver cells have suffered a death, and they've been replaced by scar tissue, and as that scar tissue developed, the liver became more fibrotic, and as that liver became more fibrotic, it became more stiff. So you have to put all of that together. Now, I'm telling you with this slide that more than just fibrosis impacts the stiffness that you get, the stiffness value in kilopascals. Other variables include portal hypertension. So what I'm saying with portal hypertension is that the blood pressure within the liver is elevated. We all know that the liver is essentially a filter, isn't it? And all of our blood, about 1/3 of our blood supply, passes through our liver every minute. So there's a lot of blood flow in the liver. And I'm sure it's no surprise to you that as the liver becomes damaged and more cells are replaced by scar tissue, that it becomes harder to get blood flow through the liver. So one of the metrics of progressive liver disease is you have diminished blood flow through the liver. In fact, one of the diagnostic tests actually looks at the blood pressure across the liver, okay, portal vein. Now, what we're saying with this is then, if you increase the blood pressure in the liver, it will actually test more stiff. So you have to be careful not to confuse increased blood pressure in the liver with stiffness and fibrosis of the liver. This is part of what a physician does when they interpret the test, because the two come together. Last thing is inflammation can affect the stiffness of the liver. See, I'm still talking about fluid buildup in the liver, aren't I? Be it blood or be it an inflammatory response in the liver. So a significantly inflamed liver will test more stiff. And again, a physician needs to be able to interpret that counterbalance between how much of this value could be due to inflammation versus how much of this value could be due to fibrosis. And that's why interpreting these tests requires physician-level knowledge and more information than this test alone can provide. This is a summary publication for anyone that's looking for something kind of technical, a physician level, that really summarizes all that's known about this test and its clinical application. This is the best review article that presently exists, and this review article is written by Dr. Nid Afdal at Beth Israel in Boston. His team has been involved with this technology since we first made the decision to bring it into the United States and submit it to the FDA, and his team has done in excess of 10,000 of these studies over the last 8 years. This is a summary table that comes from that peer review article. Yes?
Can you spell the doctor's name of that?
A-F-D-A-H-L. Nezum, N-E-Z-U-M, Afdal, Beth Israel, Boston. This is a table that comes from that publication, and what he's done is he's pulled together the hundreds of peer-reviewed publications that have happened over the years, sorted out what he thinks are the most relevant and reliable for each of the respective disease groups, and he's published that these are the values he uses in his lab. But again, I wish to stress, none of this is literal because it has to be interpreted in context. So you'll notice cholestatic has its own line here. Okay. I want to talk a little bit about some relevant literature. Before I came here, I took a little bit of time to search the literature for PBC and PSC publications. I must say there's not a lot of them, but I did want to cite what I was able to find. This is a publication that I will explain with just 1 or 2 slides, and this includes 100 patients, and 28 were PSC, 73 of which were PBC. And what they did was they compared to biopsy, came up with what they thought would be good thresholds of the various disease, levels of liver damage, liver stiffness, as you will. These are the Medivir scores from biopsy, and these are the equivalent values in kilopascals from our FibroScan VCTE test. You will notice these very closely match the slide I was showing you previously, but a couple of these thresholds are about 0.2 kilopascals different because they reference different groups, different study groups. Okay. Then they looked at what is the accuracy of the FibroScan VCTE test compared to biopsy. If you apply these thresholds, how accurate is the test, specifically in cholestatic liver disease? And you can see that they're finding, again, it's a little less accurate with lesser damage, and it's more accurate with more severe damage, the usual scenario. And you can see that we're ranging from about 96% accuracy down to 92. So that's my single point of reference specifically in PBC, PSC in terms of show me a piece of science that says the device is accurate in this specific disease group. Okay, now the other thing that the same author did, this is a newer piece of science. These are fancy letters. This is the European Liver Society, which is held annually somewhere in Europe. This is last year's, last spring's meeting. It was in March. And this is the latest information. And what the team was doing in this one was they were looking at the prognostic capability of the test. Now, by prognostic, I mean, can this test somehow predict outcomes? Can it predict patients that are the most likely to progress more rapidly, and therefore they should be more intensely monitored and more intensely managed because they're at greater risk of progressive liver disease? So let's take a look at this. There are 168 patients in this. This again is a mix of PBC, PSC. And what they did was they followed patients on average for 3.9 years. So what you have is a group of 168 patients that received this test approximately once per year for 4 years, and then they looked at the trends to see if there was anything predictive in the test. And what they found was, I'll explain this because it's kind of a complex science slide. What they found was the patients that had their liver stiffness progress slowly had a better prediction of a good outcome. The ones that progressed rapidly, on the order of 4 kilopascals per year when tested once a year, had the worst outcomes. Now, there's probably no surprise there, but these are the kinds of things you have to prove in science. You have to prove, one, that the test is reliable as compared to other tests that you have. And if you're going to be using a test to monitor the disease and try to predict outcomes, you got to prove that the test is capable of doing that. And that's what this paper is saying. Okay. A little bit about how the exam is done. Let's dismiss all this science stuff and just talk. If I had one of these tests done, what would they do to me? All right. First of all, the patient is merely lying down. You notice this patient is extremely comfortable and happy to be receiving the test. And as I'm sure you always are anytime you have a test. I know I am. Okay. And you can see that the patient's top is just rolled up so that we have access to the liver on the right-hand side. That, for those of you that are still in the wrong lecture, that's where the liver is located, right underneath there. And so what we're going to do is, you don't care about this slide, is we're going to put the patient in this position. We're going to locate or approximate where we think the liver is located, and then we're going to do some testing to be sure we're in the right place, and then we're going to take some measurements. Now, this is where the right place is. We want to locate our probe in the intercostal space. That's a rib, and that's a rib. Notice the probe is halfway between two ribs. We have to take our measurement right through that little window there. And so it is through here that we're going to send that little shear wave and then measure how fast it goes. And we're going to get all our data right there in the middle of the liver. Okay, so we locate this by merely operating off of the tip of the breastbone and then going to the right lateral midline. And then we make a decision on which probe to use. You probably are aware of this, but if you touch the surface of your skin, your liver is some distance below that. There's subcutaneous tissue between the skin and the liver. Now, with some of us, that subcutaneous tissue looks like that, and in others of it, it looks more like that. And I could probably add a fourth and a fifth and just keep moving that probe further away from the liver, couldn't I? But the point is, you change probes based on how far away the liver is. And we know how to do that. So where we're doing our assessment is in this window, between 25 and 65 millimeters below the surface of the skin, and we are assessing the stiffness of 3 cubic centimeters of tissue. So imagine we're testing a cylinder in the middle of your liver that's 3 cubic centimeters of volume. That is a very large sample. We do that because the liver, to some extent, is not homogeneous. If you test it here, it'll be a little different than if you test it just a little bit over there. So the way that you offset those differences is you test a large sample and you report the average. And give you some idea, that's 100 times the amount of tissue that's sampled in a biopsy. In a biopsy, they can't take more tissue because there's too much risk of a bleed. Because we're non-invasive and painless, we can test a large volume. Okay, so the test sequence is we locate the probe over the center of the liver. We're going to refine our position as necessary based on what the device is telling us. Then we're going to take 10 measurements. So there'll be 10 little vibrations that the patient will feel. Each one of those is a shear wave, and we're measuring its speed. We then look at the quality of those measurements on an instrument panel, and we quantify the values across those 10 measurements. So all of that I just described takes about 5 minutes, and it's completely painless. And so this test is routinely used on a standard basis anytime we have new patients that are newly diagnosed with some sort of chronic liver disease, and then it's routinely done on a regular basis that matches whatever their clinical situation is. So that's the fundamentals, and I'm ready to take questions if we have any. Hopefully none of these are too hard.
You've already answered. Let's see. This one is the only one I missed.
Okay, I've got a question on hemangioma. I can't speak to that. I don't have any specific experience with that. I can tell you there's 2 places we get concerned. One is if there's significant inflammation, ALTs are above 80. And the second one is if the patient has ascites, which is a fancy name to say they have a lot of abdominal fluid. As you might guess, you can't induce a shear wave correctly and measure its speed in a fluid-filled abdomen. So obviously, if a patient has ascites, there's other more urgent issues than assessing the stiffness of their liver. Okay. Can the FibroScan identify a patient as stage 1, 2, or 3? Those are stages specifically related to PBC, and appreciate all we're doing is measuring secondary effects of that disease. We're just measuring the stiffness of the liver, and I've already explained the 3 variables that affect that value. So we don't have any specific capability for PBC diagnosis. How important is operator consistency in doing this test? That's an excellent question. My team actually does all of the training across the country. So in order for a clinician to be able to do this test, they have to be trained and certified as competent. And my team is the one that does the training and the certification. And we're very careful not to certify anyone that we have doubts about in terms of their capability. Secondarily, I would also say that interpretation of these values is always done by a physician. So there's 2 passes over one of these tests. First, it's performed by a certified clinician trained to do the test, and they're satisfied that the test is well done and the values can be trusted, or they would not be sending it to the physician. Secondarily, the physician is trained on how to review these studies and to further challenge the data set before they interpret the values. So hopefully that answered the question. Can you use it for breast fibrosis? That's actually a very good question, and the answer is no one sorted out how to do that, but I think that's a potential viable application. I will also mention as an aside, there's early stage research being done looking at pancreatic stiffness. The initial evidence is that stiffness or fibrosis in the pancreas may be the canary in the coal mine, and it may be an earlier warning of the development of progressive liver disease than even liver stiffness is. So that's one of the things I said, invite me back in 3 to 5 years, I might be able to tell you more. Give me at least 5 on that one, maybe a little bit more. Hopefully I'm good for that many. Tumors, cancer, absolutely no value in cancer and tumors. The obvious test of choice, if you're considering things like liver cancer, hepatic cancer, that's the role of things like MRE and things like ultrasound. Please appreciate this is not an imaging test, this is a stiffness test. And so a stiffness test is not the test you want if you're trying to characterize or establish the presence of any sort of cancer or adenocarcinoma. How many centers can do FibroScan? These are great questions. I should have handed these out in advance to be sure they came to me. We have one more. We're establishing 1 to 2 new centers a week, just to give you an idea of the activity level. The FibroScan has been on the United States market for only 14 months, so this is pretty new. If you'd invited me last year, we would just be coming out of the gate with this thing. As of last week, I did a count, and there were 80 centers in the United States that had the capability to do the test, plus there's other research sites above and beyond that. For anyone from a patient perspective who's interested in finding a center that has the capability to perform the test, and pardon me, this is not intended to be commercial. If you go to the website www.fibroscan502touch, no spaces, no dots. FibroScan, that's FIBROSCAN 502 touch, TOUCH.com. There's a patient section in there, and you go to a tab that's called Find a FibroScan. There's a map of the United States in there. Every center that has a FibroScan is in there, and the telephone number to call to get an appointment as a patient is in there. And we're constantly, every week, that website changes as we add more centers, because we know patients need to be able to cut through the fog and actually find someone who can do this test a reasonable distance from where they live. What's the effect of hepatic cysts? If there were significant cysts, I would expect that it would very much show up in that. If you remember that map I was showing you that was showing the shear wave moving through, that would very much be interrupted, and we would see that, and the first thing the clinician would do is refer you for an imaging test, because that's the test you really need. Is this different than ultrasound? Another good question. Appreciate ultrasound can be used for 2 things. What it's usually used for and what you know it for is as an imaging technique. And anytime anyone says ultrasound, people think imaging. They're looking at an image. They're looking for anatomic abnormalities here. That's absolutely correct. Appreciate we're using ultrasound only to measure the speed of a shear wave. So yes, our technology includes ultrasound. No, there is not an image. Okay. I had 4 tests in one day. I scored 12.9. That's a liver stiffness score. It's not a test score, okay? He did 3 more. What I'm seeing here in the note that was passed to me was there was highly variable results, ranging all the way from 5.7 to 12.9. What that tells me is they were having some difficulty doing the test, and they were moving their position around and testing different positions. I can't comment specifically on what was going on because I wasn't there and I haven't seen the test. But generally speaking, if you have highly variable results, it means you need to work on your technique a little bit, and usually the lower score is the right score, I will tell you that. But don't take that any further than that. Usually variability is not a good thing in diagnostic testing. It means that you need to work on it a little bit. And some people are hard to test, so appreciate that. Do you have any ballpark idea? Medicare. Oh my gosh. This was the last question that I intended to seed in the audience and have come up to me. So congratulations, you got them all. Part of my responsibility is dealing with national reimbursement policy related to the test. And let me just explain some fundamentals of how medical tests are reimbursed in the United States. Anytime you have a test, there is a number, it's called a CPT code, that describes what test you received, and that test means that whoever performed the test can get paid in proportion with the effort and complexity of what they did. That's how our fee-for-service medical system works, right or wrong. We won't get into Obamacare and all that. So when a new diagnostic test is introduced to the United States, only after the test receives FDA clearance can any effort be made to get a code for the test. So what I'm telling you is the whole process of getting through FDA, proving that your test is useful and that your test is accurate, that's a completely separate process that's done first. And then secondarily, the process begins to justify having the test receive a code. I testified before the American Medical Association in April. It was our bid for a code was supported by AASLD, the Liver Society, and by the American Gastroenterology Association. We were successful. We're being awarded a code, and it becomes active in January. So that's very, very good news. Do you need a physician referral? Yes, this is a medical test, hence it's controlled. It is done only under the order of a physician, and the test results are interpreted only by a physician, as it should be. Are you Casey Kasem's brother?
That's the last one.
I wish I was, because I might have made the will. But I guess none of the other family members did.
Maybe not.
Okay, thank you.
I've got something for you here. Just a second. That was perfect. Is there something, Jerry? Thank you so much. Appreciate it.